In the last lecture, we saw what is meant by a removable singularity of a function f. We observed that an isolated singularity is a removable singularity if and only if it is locally bounded. We also noted that if an isolated singularity z0 is a removable singularity, then the limit as z going to z0 of f of z should exist. By considering the behavior of f as z goes to the singularity, let's now study the other types of singularities that can occur. The first one that we will be discussing is what is called as a pole of f at a given singularity z0. So let's start with z0, a point which is an isolated singularity. Recall that z0 is an isolated singularity of a function f if f is holomorphic in a punctured neighborhood d z0 or minus z0. We don't know about its behavior at z0. We say that z0 is a pole of f. We say that f has a pole at z0. If the limit as z goes to z0 of the absolute value of f of z, this limit, if you consider, this blows up. This is equal to infinite. Rewriting this, i.e., given any m positive, given some m positive, there exists an epsilon positive such that the absolute value of f of z is greater than m for all z in d z0 epsilon minus the point z0. If this happens, we say that the absolute value diverges to infinity. And if this happens, if the absolute value of f of z blows up as we approach the singularity, then we say that f has a pole at z0. Let's go back to the examples we did have in the last lecture and revisit them. If you look at the example which was f of z given by cos of z by z, remember that 0 was an isolated singularity. And we also noticed that the limit as z goes to 0 of absolute value of cos of z by z, this blows up. And that is precisely how we had eliminated this as a removable singularity. This was not a removable singularity because this limit should have existed. That's how we had checked that this is not a removable singularity. But this is exactly the situation which tells us that the function f has a pole at 0. F has a pole at z is equal to 0, z0 equal to 0. How about the other example? If you recall, so this is the other example which was basically e to the power 1 by 1 minus z. Recall that f of z equal to e to the power 1 by 1 minus z did not satisfy the conditions for z0 equal to 1 being a pole. So let me just write that does not have a pole at z0 equal to 1. This was because we took a sequence Zn and Zn prime in the last lecture, and we saw that the limit as z goes to Zn, if you look at the limit of f of Zn as n goes to infinity, that was 1, which was not blowing up. In fact, the limit of Zn prime as n goes to infinity of limit of f of Zn prime as n goes to infinity was in fact I, which is again it's not blowing up. So this is certainly not a pole. Of course, it's not a removable singularity either. So these are examples of isolated singularities which are neither removable singularities nor poles. Such singularities are categorized as what is called as essential singularities. Let me just write that down. Essential singularities. So, these are precisely those singularities which are neither removable nor poles. So, let Z0 be an isolated singularity of f, then Z0 is called an essential singularity of f if it is neither a removable singularity nor a pole of f. So, any isolated singularity which cannot be categorized as removable singularity or a pole is just called as an essential singularity. Let us now spend some time studying how the poles of a function f behave, how the isolated singularity called pole can be studied better. So, let us revisit our definition. So, let Z0 be a pole of f. So, that means that i.e. limit as z goes to z0 of the absolute value of f of z, this is infinite. In particular, there exists an r positive such that on dz0 r minus the point z0, if you look at that punctured disk, there exists an r such that f of z absolute value will not be 0 and hence f of z is not equal to 0. This can certainly be arranged because the limit is after all blowing up, right? By very definition we can arrange for this. So, in particular if you define a function g of z defined to be 1 by f of z on dz0 r minus z0, this is a holomorphic function, is holomorphic on dz0 r minus z0. But then by the very definition, z0 turns out to be an isolated singularity of G. Then z0 is an isolated singularity of G. Moreover, we can arrange for our capital R to be such that mod of f of z is greater than m. So, let R positive be such that absolute value of f of z is greater than m on dz0 r minus z0. Remember that the absolute value of f of z blows up as we go to z0. So, this is the exact definition, right. So, this means that absolute value of g of z, which is equal to the absolute value of 1 by f of z, that is less than 1 by m on dz0 r minus z0. That means that it is a bounded function here, it is locally bounded, or rather in fact it is bounded on dz0 r minus z0 by Riemann removable singularity theorem. Z0 is a removable singularity of G. And it is going to be a simple exercise for you to sit down and check that as we approach Z0, G of Z approaches 0. So, it is an exercise to sit down and check. You have to use the fact that Z0 is a pole of F to conclude that limit as Z goes to Z0 of G of Z is equal to 0. So, hence what do we have? G, maybe I should just change it to something else, H of Z defined to be equal to G of Z on dz0 r minus z0 and 0 on for z is equal to z0. If you consider this function h, then h is a holomorphic function. Also, since h is not identically equal to 0, that is because g is not identically equal to 0. Since h is not identically equal to 0, by the principle of analytic continuation, there exists some m such that the mth derivative is not equal to 0. Certainly, the function h vanishes at z0, let m be the first positive integer, m plus 1 be the first positive integer, such that hm does not vanish. So, by factorization theorem, let me just write that by factorization theorem and the principle of analytic continuation, this we have done many times, this particular technique that we are going to implement, principle of analytic continuation, both tell us that h of z is equal to z minus z0 to the power m times h1 of z, where h1 of z0 does not vanish. So, we can certainly write our function h of z in this manner for m greater than or equal to 1. Certainly, it will be greater than or equal to 1 because we know that h of z0 is equal to 0. So, this is certainly assured. We say okay, so let me just write down what the implications of this are. What was h of z, by the way? H of z is hence on dz0 r minus z0, h of z is just g of z, right? We have g of z is equal to z minus z0 times h1 of z. But what was g of z? G of z was nothing but 1 by f of z on dz0 r minus z0, isn't it? And therefore, by reducing our radius r further down, we may assume, let us just assume that h1 does not vanish in dz0r. We can always do that because h1 of z0 is not equal to 0, and by continuity it does not vanish in a small enough neighborhood. So, we may assume that r is exactly that neighborhood. So, we may assume, if you do not want to have any confusion whatsoever, you can go down to an r1 less than r, if needed less than or equal to r, such that h1 of z is not equal to 0 on dz0 r1. Let me not unnecessarily incorporate more notations. Let me just write that h1 of z is not equal to 0 on dz0 r. Remember that h1 is defined on dz0r, right, because h is defined everywhere on dz0r, and therefore we can always assume that h1 does not vanish on dz0r. That is good because then we can write f of z to be equal to 1 by, or maybe let me give 1 by h1 some name. We already took g, so let h0 of z be equal to 1 by h1 of z, which is now a holomorphic function, which is holomorphic on dz0r, because we are inverting a function which does not have a 0 at all. And we can now write f of z to be equal to h0 of z by, I missed an m here, so this is going to be z minus z0 to the power m below on dz0r minus z0, only places where we can talk about 1 by z minus z0 to the power m, which is away from z0. So, here we will be able to write something like this. But then h0 is a holomorphic function on dz0r, in particular its complex analytic. Since h0 is complex analytic, as you can see, I am freely using all the results that we have proved in the last few weeks. Because it's complex analytic, we have h0 of z is equal to summation a m, maybe I should write it a little more carefully. Let me write it as a m plus a m minus 1 z minus z0 plus a m minus 1 z minus z0 to the power m minus 1 plus summation a m z minus z0 to the power m, or maybe a n z minus z0 to the power n greater than or equal to n. So, we can certainly just manipulating the indices to suit what we want to write in the end. This is just the usual power series expansion that I have written down. Z0 can be written in this manner as a power series expansion around Z0 in dz0r, where it is holomorphic. And therefore, what was our f? F was h0 of z by z minus z0 to the power m. So, hence on dz0r. So, notice that here where am does not vanish. This is because h0 of z0 is not equal to 0. And because of that, we can write on dz0r minus z0, we will be able to write our function f of z. What was our f of z? F of z was h0z by z minus z0 to the power m, which is equal to am by z minus z0 to the power m plus all the way up to a1 by z minus z0 plus summation n greater than or equal to m a n z minus z0 to the power n minus m. This is precisely what we will be getting. If you notice this, if you call it something, maybe h0, h1, everything is taken, so let us call this as g1 of z. Notice that g1 of z is going to be a power series which converges. So, observe that g1 of z is a holomorphic function on dz0r because it has a power series expansion there. That is good. So, here we know that am is not equal to 0. So, the function s of z given by am by z minus z0 to the power m plus up to a1 by z minus z0 to the power 1, which is z minus z0, this particular function is called the singular part. So, this function, if you notice, is defined on dz0r minus the point z0. This is called the singular part of f around the pole z0. Moreover, this number m is called the order of the pole at z0, and m is called the order of the pole at z0. So, we have given a good description of how our function f behaves in a neighborhood of a pole of the function.